In the second activity this week, we'll be gaining a better understanding of stereochemistry through completing a series of stereochemistry stations. But let's begin by looking at what stereochemistry is. Stereochemistry is derived from the Greek word stereos, which means solid, and it refers to chemistry in 3 dimensions. So when we're talking about stereochemistry, we are looking at the ways that atoms are connected in 3-dimensional space. Stereocenters are any atom in a molecule bonded to 3 or more atoms, or 4 for carbon, for which exchanging 2 groups which are attached to it would create a stereoisomer. So, for example, if I were to exchange this hydrogen and this hydroxyl group, the resulting molecule would be a stereoisomer, which I will explain shortly. But if I were to exchange these 2 methyl groups, the resulting molecule would look and be the same, and therefore this is not a stereocenter. Similarly, the carbon of the carboxylic acid is not a stereocenter due to only 3 substituents attached, as carbon stereocenters must be bonded to 4 different atoms and be sp3 hybridized. So, as promised, let's look at what isomers actually are. Isomers are compounds which have the same formula but contain different arrangement of atoms in the molecule, which can be either constitutional isomers, in which the atoms in the molecule have different connectivity. For example, looking at isopropanol and ethyl methyl ether. Or they can differ in their position in 3-dimensional space, as we saw with those stereocenters example, and they can be stereoisomers. As a reminder, stereoisomers are compounds with the same molecular formula, but they vary in spatial arrangements. One type of stereoisomer is an enantiomer, which is a pair of non-superimposable molecules which are mirror images of each other, such as your hands. So what non-superimposable means is it's a big word that means you can't stack them directly on top of each other so that everything would align. So looking at your hands, they are mirror images, but no matter how you rotate or try and stack them, you cannot make them line up exactly. Now, enantiomers are very important because different enantiomers can behave very differently. For example, in the 1950s, thalidomide was given to mothers for morning sickness. Yet, while one enantiomer treated morning sickness, the other enantiomer resulted in the babies having physical deformities in which they were missing arms or legs. In terms of chirality, a molecule is chiral if its 2 mirror images are not superimposable in 3 dimensions, meaning if you rotate it, you can't get them to stack on top of each other. Take, for example, these 2 molecules, each containing a carbon attached to 4 substituents. Due to their arrangement, no matter which way I try to rotate them, they will not be superimposable. However, they are mirror images of each other just like our hands, and therefore they are chiral. This leads us to discussing chiral centers. A chiral center is an atom that has 4 different groups bonded to it. Chiral centers can be classified as having either an R for rectus or an S for sinister configuration using the Kohn-Engel-Prelog rules. When the hydrogen or lowest priority group is pointed backwards, if the orientation of the priority groups goes clockwise or circles to the right, then we classify it as having an R configuration. If it goes anti-clockwise or circles to the left, we can classify it as having an S configuration. The relationship between these would be enantiomers, just like the relationship between the 2 thalidomide molecules. Molecules which contain multiple chiral centers have the possibility of containing non-mirror image stereoisomers, which are known as diastereomers. Looking at this example, molecule A has an RR configuration and B has an SS configuration, so those 2 would be enantiomers. However, if you look at C, it has an SR configuration, So it would be a diastereomer to A and B because it is not a mirror image of either of those. Compound D has an RS configuration, so while it would be an enantiomer to molecule C, it is a diastereomer to A and B because again it is not a mirror image of those. In addition to the possibility of diastereomers, molecules containing multiple chiral centers can give rise to mesocompounds. Mesocompounds are compounds with an internal plane of symmetry and can be identified as having one R and one S configuration when the chiral centers are assigned. So looking at the first two compounds, is compound A meso? How about compound B? So compound A is meso, which can be initially observed due to the plane of symmetry and subsequently through assigning R and S configuration. Compound B, on the other hand, does not have an internal plane of symmetry and has an RR configuration and is therefore not meso. Finally, let's talk about axial-chirality. Axial-chirality arises from the non-planar arrangement of four groups in pairs about a chiral axis, and because of this, it doesn't require a chiral carbon for the molecule itself to be chiral. It's typically encountered in allenes and ortho-substituted biphenyls, such as those shown. So what axial chirality is chirality of a molecule due to lack of free rotation because of steric hindrance, because of big bulky substituents, or rigidity due to double bonds. So looking at these two biphenyls, they do not contain any chiral carbons. However, due to the rigidity of the molecules due to the steric hindrance from the large substituents, the position of the bonds are held in place. Therefore, the biphenyls cannot freely rotate, and so when we're looking at them, we can see that they are mirror images of each other, and yet they are not superimposable, and therefore they exhibit axial chirality. When determining the number of predicted stereoisomers, it is useful to have a method to calculate how many there are predicted to be. For example, if a molecule has one chiral center, then it can have two stereoisomers. Two chiral centers can give rise to 4 stereoisomers, 3 give rise to 8, etc. Therefore, the equation for determining the number of stereoisomers is 2 raised to the nth power. Finally, to review, if two molecules have the same molecular formula, but they differ in arrangement, they are called isomers, which can be constitutional, in which the arrangement of which atom is bonded to which changes, or they can be stereoisomers, in which the position in space that those atoms are arranged differs. If they are stereoisomers, they can be diastereomers or they can be enantiomers. Now, it is important to remember that when you say diastereomers or enantiomers, you are referring to the relationship between two molecules. You can never say that one molecule is just an enantiomer. It is an enantiomer to another molecule. Diastereomers have a non-mirror image relationship, so they can be something like an RS configuration with another molecule that's an RR configuration. Enantiomers are non-superimposable mirror images, so they could be something such as one molecule is an RR, and its enantiomer then would be an SS.